In this video, we're going to work through a few problems that involve the ideal gas equation. The ideal gas equation is PV equals nRT. This is saying that the pressure of a gas in units of atmospheres times the volume of a gas in units of liters is equal to the number of moles of gas times the ideal gas constant, which I'm going to write down in just a second, and the temperature in units of Kelvin. The ideal gas constant is just a constant that turns the relationship between pressure and volume and moles and temperature into an equality, and its value is 0.08206 liters times atmospheres over moles times Kelvin. It's a pretty simple equation to use. Typically, you are going to be given 3 of these 4 variables that I've highlighted. Typically, you're not going to be given the value of R because it's a constant. You're expected to know that and just plug it in. So you'll be given 3 of these variables. You know the value of R, and you'll be asked to solve for the 4th variable. Let's take a look at problem number 1. This says we have a sample of gas in a 2.5 liter container. So that is our volume. It has a pressure of 0.7 atmospheres, so that's our pressure, and a temperature of 28 degrees Celsius. That temperature is in the wrong unit, so we need to convert it into kelvins. 278 plus 273 will give us the temperature in the correct unit. 278 plus 273 is 301, and it's asking us to calculate the number of moles of gas. So let's take the ideal gas equation, PV equals nRT. You have 2 options. The number of moles, first of all, that's our unknown. That's what we're trying to solve for. We have 2 options here. We can plug everything in and then solve for n, or we can begin by rearranging this equation to isolate the n variable and then solve for n. I'm going to, for this first example, just plug everything in. Our pressure is 0.75 atmospheres. Our volume is 2.5 liters. N is the unknown variable. R 0.08206 liters, atmospheres, moles Kelvin. You might see the value of R as 0.0821. That's just 3 sig figs instead of 4. Temperature is 301 Kelvin. And if we take a look at all of our unit cancellations here, we're going to get atmospheres canceling, liters canceling, Kelvin canceling, and we will end up with units of mole. So to solve for n, we'll go 0.75 times 2.5, and then divide that by the right hand side, 0.08206 times 301. That gives us if I did my math right, 0.0759 moles. Let's take a look at the next problem. This problem says that we have a 1.5 liter container of gas at STP that is heated to 100 degrees C. The container doesn't change volume. What is the final pressure? So this is a little bit different than the first problem. This is a problem where we have variables that are changing for the gas. The gas is being heated. And so when we have a changing variable situation, we want to use a different form of this equation. P1 V1 over N1 T1 equals P2 V2 over N2 V2 T2. So this is called the combined gas law. In the combined gas law, this allows us to account for any of these variables that are changing under whatever conditions we have. So again, let's go through the problem and kind of isolate or identify what our variables are. It says we have a 1.75 liter container, so that's going to be our V1. It is a gas at STP. STP is standard temperature and pressure. So standard temperature, this is our initial temperature, is 0 degrees Celsius, which is 273 Kelvin. And then our standard pressure, P1, is 1 atmosphere. It tells us that it's being heated to 100 degrees C, so that's our T2. Our T2 is going to be 373 Kelvin. The container does not change in volume, so that means that our final volume is equal to our initial volume, and this wants to know what the final pressure is of the gas. So P2 is the unknown variable. In this combined gas law equation, any variable that is not being changed at all does not need to be included in the actual calculation. So when this tells us that our V1 is equal to our V2, we're actually able to just cross that out completely from this equation. And you might wonder, how is that mathematically allowed? Well, since the volume is not changing, we're just going to be having 1.75 and 1.75 on both sides of the equation, so mathematically they'll just cancel out. Also, in addition to that, if we're not given any information about one of the variables, for example, we're not being given any information about the number of moles of a gas, we can always assume that that means that that variable is unchanging as well. It's constant, so we can cross that off as well. And this leaves us with a simplified equation that says P1 over T1 equals P2 over T2. And we can go ahead and plug our variables in. P1 is 1 atmosphere. T1 is 273 Kelvin. P2 is our unknown, and T2 is 373 Kelvin. 373 times 1, so I'm using this math relationship right here. 373 times 1 divided by 273 gives us a final pressure of 1.37 atmospheres. This looks like another similar problem. We have a sample of gas in a flexible container. The term initial pressure and initial temperature, this just immediately tells me that I want to use this combined gas law. P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Again, this is the equation that we're going to use anytime there's any sort of change going on. And the word initial tells me that there's going to be some sort of change going on. Initial pressure and temperature of 1.25 atmospheres. So this is my P1, and my initial temperature of 50 degrees Celsius. That's my T1, and I'm going to convert that straight into Kelvin. 323 Kelvin. It was heated to a temperature of 65, so that's my T2. Convert that straight into Kelvin. 65 plus 273 is 338. This caused the pressure to increase, so that's a P2. The final volume was found to be 500 milliliters. So this is our V2. And remember, our volume should be in units of liters, so we'll divide by 1,000, 0.5 liters. What was the initial volume? This is the variable that we're trying to solve for. The problem doesn't tell us anything about the number of moles, so we can eliminate that from the equation under the assumption that moles do not change at all. And let's just go ahead and plug in the variables that are given to us. P1, all the way up here at the top, P1 is 1.25 atmospheres. V1 is our unknown variable, and T1 is 323 Kelvin. P2 is 1.7 atmospheres. V2 is 0.5 liters. And T2 is 338 Kelvin. And so we just need to solve for V1. I'm going to do all the math on the right-hand side first. 1.7 times 0.5 divided by 338. And then I'm going to take that number and I'm going to divide it by the right-hand side. 1.25 divided by 323. And I get an initial volume of 0.6498 liters. We have one more problem on this worksheet. This is a gas density question asking us to calculate the density of gas. I don't know what happened here. It looks like there's some extra words copied into the end of this problem. We can ignore that. The equation for determining the density of a gas is the molecular weight, which I'm just going to abbreviate MW, the molecular weight of the gas times the pressure of the gas divided by the gas constant R and the temperature T. So we need to know the density of the hydrochloric acid HCl gas. We can get that just by adding up the molecular weight, the atomic weight of hydrogen plus the atomic weight of chlorine, which is about 36 grams per mole. We'll say 36.5 grams per mole. I'm going to multiply all of that by the pressure in units of atmospheres, 0.95 atm. The ideal gas constant, 0.08206 liters atmospheres over moles Kelvin, times the temperature in Kelvin. 42 plus 273 is 315. These problems are, density calculation problems are pretty straightforward. Just they're long because there's so many units. 36.5 times 0.95 divided by 0.08206 and divided by 315 gives us a density of 1.34. The units of density for a gas are grams per liter. We can just kind of take a look at how these units cancel and see that we end with grams per liter.